Introduction to implementing qubits using continuous quantum states. Overview of continuous quantum states. Quantum information processing uses qubits as the fundamental unit, analogous to classical bits. While classical bits take values of 0 or 1, qubits exist in a superposition of these states, enabling unique computational capabilities. Traditional qubits are implemented with discrete quantum states, such as the spin of an electron or the polarization of a photon. However, continuous quantum states provide an alternative approach by utilizing continuous variables such as position or momentum. In continuous quantum states, information is encoded in variables like the quadrature amplitudes of an electromagnetic field. These systems have distinct advantages. Robustness against noise. Continuous states can be more resilient to noise and incoherence due to their inherent redundancy. Applications. They are particularly suited for quantum communication and cryptography, encoding qubits in continuous variables to represent a qubit using continuous states. Quadrature amplitudes of an electromagnetic field, denoted as x and p, are used. Here, x is analogous to position and p is analogous to momentum. Quantum operations are performed by manipulating these quadratures. Techniques for manipulating continuous qubits. Beam splitters mix different quadrature components, enabling operations like rotations and entanglement generation. Squeezers enhance measurement precision by reducing uncertainty in one quadrature at the expense of the other. Homodite detection measures quadrature amplitudes with high precision, providing information about the quantum state for further manipulation or tomography. Applications of continuous quantum states. Quantum key distribution, secure communication protocols utilizing continuous variables. Quantum teleportation, transferring quantum states without physically moving particles.
Schrodinger's equation for a 1D free particle, a fundamental tool for understanding qubits, is Schrodinger's equation for a free particle in one dimension. It describes the evolution of the wave function psi as I times h bar times the partial derivative of psi with respect to time equals negative h bar squared divided by 2m times the second partial derivative of psi with respect to x squared. Here, I is the imaginary unit, h bar is the reduced Planck's constant, is the particle's mass, psi of x and t is the wave function. The wave function, psi, represents the probability amplitude of finding the particle at position x at time t. Solving Schrodinger's equation gives the wave function as psi of x and t equals a times e to the power of I times the quantity k times x minus omega times e plus b times e to the power of negative I times the quantity k times x minus omega times. A and b are constants. K is the wave number, and omega is the angular frequency. The wave number k and angular frequency omega relate to the particle's momentum p and energy E as k equals p divided by h bar and omega equals e divided by h bar. This wave function captures the particle's wave-particle duality, where k and omega represent its wave-like properties while p and e describe its particle-like behavior. Are constants. K is the wave number, and omega is the angular frequency. The wave number k and angular frequency omega relate to the particle's momentum p, and energy E as k equals p divided by h bar and omega equals e divided by h bar. This wave function captures the particle's wave-particle duality, where k and omega represent its wave-like properties while p and e describe its particle-like behavior. A model for qubits. Concept of a particle in a box. A particle confined in a one-dimensional potential world box serves as a foundational model in quantum mechanics. The particle's wave function is zero at the box boundaries, resulting in discrete energy levels or eigenstates. Quantized energy levels. The energy levels are given by the formula E sub n equals h bar squared times n squared times phi squared divided by 2ml squared, where n is an integer, n is the particle's mass, and l is the box length. Wave function. The wave function is given by psi sub n of x equals the square root of 2 divided by l times sine of n times I times x divided by l. The quantization arises from boundary conditions that force the wave function to vanish at x equals 0 and x equals l. Time evolution. A general wave function is a superposition of eigenstates. Psi of x and z equals the summation over n of alpha sub n times e to the power of negative I e sub n times d divided by h bar times psi sub n of x. Here, alpha sub n determines the contribution of each eigenstate. E to the power of negative I e sub n times d divided by h bar describes the time-dependent phase factors. Implementing qubits with a particle in a box, basis states use the ground state n equals 1 and first excited state n equals 2 as qubit states 0 and 1 wave function. The qubit state is expressed as psi of x equals alpha times the square root of 2 divided by L times sine of pi times x divided by L plus beta times the square root of 2 divided by L times sine of 2 pi times x divided by L. Alpha and beta are the superposition coefficients. The energy gap between state 0 and 1 is delta E equals E sub 2 minus E sub 1, which simplifies to 3h bar squared times pi squared divided by 2ml squared. This determines the frequency of qubit oscillations and is crucial for manipulation using light pulses. Implementing qubits in physical systems. Physical systems for qubit implementation. Qubits are artificial atoms created from superconducting loops. States are manipulated using microwave pulses. Trapped ions. Qubits are encoded in electronic states of ions trapped by electromagnetic fields. Laser pulses control state transitions. Quantum dots. Combining electrons and semiconductors allows for precise control of quantum states. Photonic systems. Individual photons represent qubits, ideal for quantum communication. Topological systems use exotic materials to protect quantum states from decoherence. Challenges and techniques. Decoherence. Sensitive to decoherence. Challenges and techniques. Decoherence. Bits are sensitive to environmental noise. Error correction. Algorithms mitigate errors in quantum operations. Control mechanisms. Light or electromagnetic fields are used for precise qubit manipulation. Conclusion. The implementation of qubits is a cornerstone of quantum computing. Continuous quantum states provide a versatile framework for encoding and manipulating quantum information. By leveraging models like the particle in a box and advanced physical systems, researchers are overcoming challenges in decoherence and control to unlock the potential of quantum technology.